Good morning, good afternoon, and good evening. Welcome to the presentation of this NEO community blue paper on the NEO Persistable class framework. This will be a deep dive. There's quite a bit of code and quite a bit of code on PowerPoint slides, so hopefully you don't fall off your chair. My name is Michael Herman, and this is part of my submission to the City of Zion Distributed App Contest number 2. So what is a blue paper? A blue paper first was used or defined in Germany, and it's come to represent papers outlining only technical specifications and descriptions of new technologies or other pieces of equipment. And so what's a NEO community blue paper? It's actually a phrase I coined, and it's intended to apply to any blue paper that's written by anyone who's passionate about the NEO blockchain platform. Of course, they can be sponsored or unsponsored, and this particular one is unsponsored. Right off the top, I want to give a couple shout outs to two fellows, Sergio and Chris. Sergio's the lead contributor on NEO Debugger, and Chris is the lead contributor on the NEO GUI developer project. Both of these projects have been very key to supporting the ability to develop and debug the NEO persistent class framework. And I've been able to work with each of those guys to put some enhancements into the event log to provide some special formatting for NEO addresses and different kinds of NEO keys. And you're going to learn a lot about something called NEO storage keys. So there's some support for NEO storage keys in terms of the event log. So instead of just seeing binary strings of things coming out there, you get more of a fatted repetition. So, Sergio and Chris have been extraordinarily patient and extraordinarily helpful, and I really appreciate everything they've done. Okay, so the agenda, I've got kind of a standard format that I use. We'll talk about the purpose of this presentation a little bit more. Give you a scenario to kind of scope what it is that I'm talking about, and then within that define the problem that I'm trying to solve. We'll do some analysis, particularly of the the NEO platform and this what I call the C#.NEO language, and then look at some options relative to that analysis, find some options for addressing the problem, and then I'm going to show you the the code solution, some test results, and a bit of a roadmap. This might be as long as an hour. I don't know. I'm not doing a dry run. I usually just do these once all the way through. So we'll see what happens. Okay, a few definitions off the top. So NPC is the acronym I use for the NEO Persistable class framework. A couple key new concepts. There's the NEO versioned appuser. These are objects that are used to create NEO storage keys. I'll talk about those in detail, and I sometimes call those UVAs. There's NEO storage keys, or NSKs. These are the key technology behind the level 4 collectible classes, NPC classes. And there's also NEO Kong, and Kong stands for key object notation for geeks. That's another technology that's used to support NEO storage keys. Lastly, a few acronyms, if you want to call them that, to differentiate between the different species of C# programming languages we're going to be talking about. So C#.ms is the version of C# supported natively by the Microsoft C compiler in Visual Studio 2017, and it conforms to the C# 6.0 specification. C#.neo is the subset of C#.ms that's supported by the Neo neon.exe transcompiler, kind of as of January 2018. I don't think that's changed too much. And then I'm going to talk about a specific version of C#.neo, C#.npc, which is an explicit definition of the subset that's supported by the Neo transcompiler for .NET, and also follows some recommended and documented best practices for object-oriented contract development. So the purpose of this explanation is to explain the key drivers, behind the Neo Persistable class framework, as well as the range of design and implementation details. This is a very deep dive into the technology platform. So we'll give a complete description of C#.npc and different strategies and options for supporting object programming capabilities that are found in C#.ms but not supported in C#.neo, and then some basic guidance for, given that we don't have all the capabilities of the full C#.ms language, what can we do when it comes to doing object-oriented smart contract development on Neo? And the substance behind what I'm talking about, or the deliverable, is NPC DAP, which is the initial reference implementation of the Neo Persistable class framework. This presentation is the second in a series of 3. The first one was entitled How to Run NPC DAP, and you can find both of these on YouTube. As I was going back and looking at kind of all the probably dozens and dozens now of C# smart contracts, little C# smart contracts I've written to evaluate the C#.neo language, I was reminded that part of the inspiration came from this very simple sample that's in the Neo project /examples -C# project. So I want to give some recognition there as well. Okay, so let's go into section 2 on the scenario. And so developers on the blockchain platform have a variety of language tools, different environments, as well as other technology options to consider when developing smart contracts. C#, Python, Java, and others. And so as a scenario, this document specifically is targeting C#.neo smart contract development using Visual Studio. So continuing with the scenario, the diagram on the top right is part of the Neo blockchain architecture reference model for .NET developers. And you can find that in the MW Herman 2000 / Neo-Charm project. And one thing I place a lot of emphasis on here, particularly in this upfront part where we're doing the analysis of the platform, is you really need to understand the platform quite deeply. And so let's quickly look at that, and using the the lettered bullets there as reference. So if we think of kind of the life cycle of developing, deploying, testing a smart contract in C#, developers start by developing their code using their favorite IDE and high-level language. So in this case, it'd be C#.ms. So A represents the C# source code, let's say for the Hello World smart contract. You're editing that with Visual Studio. You're using the Visual Studio C# compiler that comes with it to create the Hello World DLL, and that's represented in an intermediate language called Microsoft Intermediate Language, which in turn would normally be compiled or down to machine code if it was a regular Windows app. But in this case, we have the Neon .exe transcompiler, the Neo transcompiler for .NET. And what it does is it reads the DLL, the MSIL bytecode patterns there, and in turn creates a hello world.abm file, which represents the Neo VM bytecodes. And then that further goes on. You can use the Neo debugger to load your AVM and to run it. And then later on, you could use Neo GUI, Developer Edition, to deploy your code into the virtual machine onto the blockchain, testnet or private net to further test your code. The thing to note is that particular flow gains incredible value from leveraging the Microsoft .NET compiler stack, but there's also a significant challenge using this approach. First of all, Visual Studio doesn't know anything about the instruction set that the VM supports, nor does the Microsoft C# compiler. C#.ms implements the full C# 6.0 specification and simply knows how to generate MSIL files for that full C# language. On the other hand, the C#.neo compiler for .NET, the neon.exe, only supports a subset of the MSIL patterns generated by the compiler. So you've got the Microsoft environment supporting the full language, but we have an execution environment, the Neo VM, and the compiler that only understands a subset of those MSIL patterns. So it becomes an interesting scenario trying to figure out at a C# source code level what patterns are supported in the C# language that in turn will be transcompiled into Neo VM bytecode and in turn will execute on the VM itself. So I call this subset of the C# MS that will ultimately be supported in the Neo VM C#.neo. And further on, we're going to describe something even more tightly, and we're going to call that C#.npc. So the questions we need to ask from this scenario is, what are the supported patterns of MSIL that Neon EXE supports? What are the good, better, best practices, to use to use C# in the Neo environment? And how do you work around what is important but not supported in C#.neo? The undocumented, if you will, version of C# that actually runs on the Neo VM. Okay, so I've already sort of hinted at the problem, but let me just knock it out here as a problem statement. Given that the subset of C#.ms that is supported by the Neon compiler, and in turn, of course, the Neo VM, is not documented, how do we proceed to exploit the capabilities of C#.neo? What are the supported patterns? What are the good, better, best patterns to use? And how do we make more tangible, beneficial use of this environment? The second major bullet there, how do we use C#.neo for sophisticated object-oriented development? That is something that is not being practiced in the community today, visibly practiced in the community today. Also, how do we support C# classes beyond just being nothing more elaborate than C++ or C# like structs? And that's about as far as you see classes being used today for smart contract work. So there's an example at the bottom. So let's start by analyzing the Neo platform. Let's look at, based on a bunch of experiences developing dozens of very short C# smart contracts, kind of what works and what doesn't work, and let's try to see if we can kind of come to terms with that subset of C# that we can use. So I have these little sidebar slides from time to time just to break up the monotony. And so I have a question for you. How is programming the Neo VM like learning to fly a flight simulator? How is programming the Neo VM like learning to fly a flight simulator? Well, if you think of the pilot sitting inside that cockpit, he or she is manipulating the controls, the rudder pedals, the stick, the steering column, dials and gauges on the inside of the flight simulator. And those are in turn being interpreted by the flight simulator and all the computers that support it to move those hydraulic cylinders around and to create visualizations on the windscreen and to create sound effects, things that are external to the flight simulator. So in a lot of respects, the smart contract running inside the VM is like the pilot inside the simulator. The smart contract doesn't know about anything outside of the VM. It only has, certain opcodes that it knows it can use, and that the VM will interpret them. Occasionally, the VM will reach, outside of its immediate world, to do things on your behalf. And so there's actually a very strong parallel or symmetry there of incompatibility, I guess, between C# MS and the C# Neo that's implemented by the Neon compiler and the VM. So going back, we're going to go across the rows now. So class constructors, parameterless class constructors are supported, and I say only for field layout. So it's only the members within a C# class that are actually recognized by the Neon compiler. And so the workaround there, if you want to do some actual initialization of those members, is to create public static and private static methods, to support those capabilities. And we'll see lots of examples later on, because this is going to seem a little bit abstract. But the idea that instead of executing the constructor, you'll call the new method on the class. This is similar to the way that the dataset and data table technology in ADO.NET works. For example, you want to create a new row in a table, you invoke the new row operation on the table, and you get a new row. You don't use a constructor. And then having an internal initialize method, static private initialize method for setting the values there when there's no parameters. Going to the second row in the table, again, class constructors with parameters are not supported. Any of those parameters are simply ignored, as is, again, the body, the third row in this table. And so the way to support that is having a new public static new method that would take, let's say, an X and a Y type coordinate or whatever values are important for initializing your entity, and then it would return the entity. In terms of logic that's in the constructor, you could create variations, but in general, the pattern we follow is every method that you execute against a class is a public static method. So here's public static foobar, and then it can have whatever parameters you want. When we talk about properties, which is implementing get and put capabilities on the fields in your class, the pattern again is to create public static methods like set the X, set the Y, get the X, get the Y, as well as having just a simple set function in which you would pass all of the values to initialize the entire entity. Null valued variables in the middle of the table there are not supported in C# .neo. So how do you implement that? So a fairly important decision was made to start including a set of what are called system fields in the definition of each class. And so a really key one is the _state field. And it's an enum that's driven by the entity state type. And we'll see a lot of that example. So then we have the ability to create null instances of a class, just like we can new a defined instance of a class. We can create null instances of a class. Then we have like an is-null test to find out if the particular entity we're working with in our code is a null entity or a real entity. When it comes to data types, floating point and integer types, floating point is not supported, and integer data types I put partially supported. When I think of what are the native C#.neo data types, it's really string, byte, and big integer. And I say that it's only those three because those are the only three that are supported from a Neo storage perspective. So the ability to store values on the blockchain, the state of the blockchain, those are the only three that are supported. I say integer types, like int and int32, are partially supported because you can use those types, let's say for indices when you're looping through an array, and those sorts of things, but you really need to convert them to big integer if you want to store them. At the bottom here, switch statements, their implementation is not predictable. So in C#.npc, we recommend against them. When I say not predictable, what I'm saying is that the C# compiler, the Microsoft C# compiler, performs different kinds of optimizations at its discretion. So sometimes it compiles a switch down to an if-then-else pattern when it creates the MSIL code, and sometimes it compiles it down to an actual switch opcode in the MSIL code. The problem is that the C#.neo compiler, the neon.exe, supports if-then-else, but it doesn't support the switch opcode. And similarly, neither does the Neo VM. So rather than take a chance, I recommend just not using that, and that's kind of part of what we consider to be part of C#.npc. Fixed-length arrays. There's probably a larger discussion here, but usually what you're trying to do is work with the data in a way that the Neo VM doesn't intend you to use it. So without going into too much explanation, the way that you work around that is you generally build up arrays, byte arrays, by using the byte concat operator. So you have an existing array, and then you can add new pieces of byte array to that. Similarly, if you're trying to manipulate the contents of an array, for example, assign to different elements of an array, either individually or in a loop, that's not supported as well. So concat generally is the solution there. In terms of different conversions to string, this is often in a scenario where you're trying to log messages back to the Neo event log. There's a couple of recommendations here that you can try. Lastly, at the bottom, enums. Enums are represented internally within C# or within the Microsoft C# compiler is ints. They are partially supported in the same way that integers and int32s are partially supported. So they're great things to use. Just be prepared to do lots of conversions from the enum to int, and then from int to big integer, depending on what you're trying to do. Okay, so those are the primary use case scenarios where C#.neo varies from C#.ms. The other part of the analysis was around looking at what sort of data type conversions are there, and the key class that helps you with that is the helper class within the Neo Smart Contract .framework namespace. So the ability to convert, strings and bytes to big integers to byte arrays, being able to concatenate byte arrays together, being able to convert hexadecimal strings to bytes. It's a very limited set, and it doesn't cover all possibilities. So it's important to understand this particular helper class. The other part of the analysis, because a key unique aspect of the Neo persistent class framework is its ability to persist objects, entities, into Neo storage, and also to be able to bring those back and deserialize them. So here, the interface to that underlying storage is through the storage class of the framework services.neo. And we have the get, put, and delete methods. And you can see on the right here that there's really only support for bytes, big byte arrays, big integers, and strings. And when those are returned, they're returned to you as byte arrays. So this is all wrapped up and encapsulated in the internal implementation of the NPC framework, so it's not generally something you have to concern yourself with. I've also highlighted that there's some delete methods. In this first version of NPC, I actually wasn't aware that there's a delete method. So delete actually isn't supported, but we have something else we call bury. We actually implemented an alternative to delete. We call it bury, which uses a tombstoning approach to accomplish a similar thing. We'll probably end up leaving both of them in there. Delete has been put on the roadmap for the next version. Further analysis was trying to understand all the different types of sort of Neo-specific things like addresses and accounts and public keys and private keys. And this is just a summary slide that was created from that research and might be helpful as people are trying to understand the Neo platform from a C# perspective. Another sidebar. So if previously we looked at an architectural slide that described the Neo development environment, this is the left side of the larger picture. This is the Neo virtual machine. And you can see in the green box there, that's the execution engine. That's the cockpit that we talked about before. That's where your Neo bytecode scripts run. And it's a sandbox, and they run securely and safely within that. The only things that they're allowed to use are those services across the bottom below the interrupt service layer. So there's a formally defined interrupt service layer, and there's a formally defined set of services. So you can access, for example, storage, the box marked X. You can access blocks on the blockchain using the service marked S, and runtime services, the box marked U, allows you to log messages onto the event log. So the Neo virtual machine environment is very well architected, fairly straightforward to understand. So all of that analysis that we've just finished around the language and what's supported and what's not supported, it's about what runs inside of that box labeled H, the execution engine. And the kind of key message here is we've started to create a formal definition, an explicit definition of the C#.MPC language. And that's the subset of C#.MS that is supported by the Neo transcompiler for .NET. And it follows recommended and documented best practices that you'll find in this document. C#.Neo remains the label for the implicit or undocumented definition of the version of C# that's supported by the transcompiler. Okay, so let's look at our options, our solution options for addressing, the problem of we've got this differences between C#.Neo and C#.MS. We've done that analysis. We understand the discrepancies. So what is it that we're actually have available to us as options in terms of coming up with a solution? Now, in this case, the options are few, and in most cases, the options are singular. There's only one of them. So this section actually starts to document the solution in terms of what to use, in terms of what works, and what are the best things to use. So the recommendation, for example, when you're defining the fields in your class is only to use strings, bytes, and big integers. Occasionally you use ints or int32s, but strings, bytes, and big integers are the only things you'll be able to persist into Neo storage. In terms of constructors, every class should be given a private, parameterless constructor that is never used. That's just a convention that the Neo persistent class framework has adopted. Every class should have a public new and a public new XY style of constructor for creating new entities of that class. Again, that's to make up for the fact that we don't have a fully implemented support for constructors in C#.Neo. All class methods should be modeled and implemented as public static methods. The entity should always be passed as the first parameter to these public static methods. The exception today is the log and log extended methods that are used for sending messages or trace information, debug information to the event log. For null-valued variables, start by adding system fields to each class. In this particular case, the state system field that's private and of type entity type, and we'll talk about what entity type actually looks like in a bit. And that all of these system fields should be marked private, but they should have static public wrapper methods, for example, to test if an entity is the null entity or not. Use byte arrays whenever possible to minimize storage versus strings, which will take twice as much storage, as well as being the easiest way to work with from a Neo runtime library perspective. The greatest number of methods support byte arrays, manipulation of byte arrays than any other data type. Other considerations. We have a basic object-oriented, class-oriented pattern now for working with classes in C#.Neo. New methods, parameterless classes, and a way for implementing null. So we call that NPC Level 0 or basic. It's just basic class support. Once we get into the solution section, we're going to take you through what managed, level 1 managed, level 2 persistable, level 3 deletable, level 4 collectible mean, and what the actual methods are there. This is a layered persistence model. In general, we want to keep the amount of code, the volume of code, the number of byte codes in our smart contracts reasonably small. So in the Neo Persistable class framework, we've gone to a layered model. So you only implement the methods representing the functionality that you need for a particular class. If a class is never going to be persisted to storage, then it can simply be a level 0 basic class. Or a level 1 managed class. But as soon as you need to persist it, it's going to be level 2 and level 3, or level 2, level 3 and level 4. And as I mentioned down at the bottom, the primary driver for the NPC levels is minimizing code size by implementing all the levels and corresponding methods. There's a required set of basic methods required to implement each level for a specific C# class. Okay, moving on to the next major section, which is the solution. And so here we're going to actually look at the implementation of the C# NPC framework. Another sidebar. So this is the very first version of the Neo Persistable framework, Persistable class framework. And so I've got a very specific approach I use for these kinds of new projects. So on the left here, we can see we're in the version 1 is make it work. So maybe there's some things that we have to work around, or a little bit kludgy or whatever, but it's about make it work and almost make it work at all costs. From that, we're going to get some learnings, and so we've been talking about some of those learnings already in terms of defining the C#.NPC language. Then we're going to move to a make it work better and make it work right subsequent versions, and those help guide our roadmap as well. So the first step of the roadmap, make it work. Second step in the roadmap, make it work better. Third step in the roadmap, make it work right. All based on learnings from the previous efforts, and that's what I'm trying to highlight here. There's actually an article, how do we think about how we work, on my blog site, hyperonomy.com, that you might want to take a peek at. Okay, so section 6 here on the solution, i.e. the design and implementation of NPC, has several sections here, and this is probably the longest section in the blue paper. So we'll start right into that. Okay, NPC levels are basic. You just define a class. And you can create instances of that class. In fact, when you create instances of a class, this is all that Neo C#.NPC is going to do for you anyway. If you had a constructor in there, it's going to ignore it, whether it's a parameterless or parameterful constructor, or whether that constructor has an internal implementation. All you're going to get is the layout of the fields for your particular class. So moving on, what does level 1 managed mean? Well, here what we want to do is start supporting the ability to have null entities. We also want to provide some more support in terms of being able to do tracing and logging. So we have one utility class here called trace, and it's actually used by all levels. And you see a fully qualified method called notify here. One of the reasons for that is there's some overlap in some of the namespaces in the Neo libraries. So this is partly a convenience and partly a necessity. But you'd call it just the same way you would call notify if you're calling it natively. Level 1, we're looking at an implementation, a reference implementation for a point that has an X and a Y coordinate. So we make all of the fields private, and we have a convention of putting underscores in front of their name. There you can see the underscore state system field. And here you can see the accessors, the set X, the set Y, and the set that takes an X and a Y. And whenever we change the value of a field, we also set the state system field to set. And that's about all that we see here. So let's go ahead. Here we call the factory method. So there's the constructor, the parameterless constructor marked private that we don't use, and that basically hides it so it can't be used. For creating new instances of an object, of an entity, we use the new method at the bottom, the static public new method. So you'd call point.new to create and have an initialized point returned to you. And so you can see at the bottom there that it calls underscore initialize, and then underscore initialize sets the X and the Y to 0, and initializes the entity state. Here we see an example of the new method that takes parameters, and of course this sets all of the fields in the point. We could use initialize, but we're trying to be a little bit efficient here in terms of not having a whole bunch of calling going on. So we have a small number of fields, so we're just simply initializing them directly. At the bottom here, we can see how we create a null point. We just simply call initialize. Here we have the wrapper method for the state system field, where we're explicitly using it to test if it's null. So when it comes to the syntax, what our source code actually looks like when we're creating an application, we're simply doing point.null, for example, or point.new to create new instances of objects, and then we can do point.isNull, to ask if a particular object is null or not. It makes for very clean code. Similarly, a convention for all classes that are using NPC at any level is that they have a log and a log extended method. The log dumps out like the purposeful fields of the class, and log extended also will dump out any state fields. So in this case, at the bottom there you see X, Y, and state. We grow this just a little bit. We'll have 1 or 2 additional system fields as we go up through the levels, and log extended will dump those out. Okay, so that's level 1 manageable, or managed classes, and we're really supporting the ability to create new objects explicitly and the ability to test if they're null or not. The next level up, NPC level 2, is about making our objects automatically persistable. And by automatically persistable, we mean you just call the put method and pass in your point, or you call your get method and you pass in the key for your point. So we're going to see how that's implemented. So the new entity model is updated. So we've got putted, getted, and missing. Putted and getted are kind of obvious. Missing is kind of interesting because you might do point.get and pass in a key expecting to get a point back, but the point actually isn't in storage for the particular key value. So we can set the state to missing, and you can test that whenever you get something back from storage to see if it's missing or not. The 2 helper methods there haven't changed. When it comes to the getters and setters and the field definitions, those are exactly the same. But we need some additional support for the put and the get methods. And so we need to, when we take the key that we're provided, we save like the X and the Y out as separate entities in storage, as two separate entities. So we need a naming convention for how we put those out into storage. And so there's a way of concatenating the key that's passed in with the class name point and with the field name, in this case X and Y. So these definitions would be different for different classes. We also save that status with the entity. So we use underscore STA as part of the key. And then underscore EXT. This is for supporting a future capability on the roadmap called extensions. The ability for an entity to have an initial set of fields, and then for that inevitable scenario, we're going to say, I want to add some fields to this entity. So NPC, the Neo Persistable class framework, supports the idea of extension of the fields that are in your entity. And so that's kind of a cool thing. We won't talk about that too much today, but you'll see little artifacts like that underscore EXT part of the key. And we take those strings and we convert them to bytes. So this is following the best practice that we talked about before, is try to stay working with byte arrays all the time. And so this is how we do that. At the bottom there, you can see how we're starting to form part of the key. So this is for plain old string and plain old byte array keys. This is different from the higher level layers where we're starting to use Neo storage keys to manage Neo storage. So in the factory methods, these are the same. These are unchanged from before. The new and the null are unchanged from before, as are the null and log and log external methods. For these first few levels, I'm going through all of the methods in each of the classes. As we get up into the higher level definitions of NPC, I won't bore you with all of that code. So in the persistable methods, we need to support the concept of missing. So we have the entity state missing, and so we can test to see if a particular point is missing or not when we get it back from storage, and or we try to get it back from storage. And then we also have a public static method here that can create for us a missing entity, and this we need in some of our get methods. We need to return missing points or missing objects, missing entities when we're unable to find it in storage. So this is what put looks like. So we test the key right away to see if it's 0, and if it's 0, we're going to return false. We're going to get a handle to the context because we're going to execute puts against the context 4 times at this level, so it makes sense to save it. This is the keys that are based on bytes there. You can see that in the top line of the code. And so what we're going to create is a binary, what we call a key tag. So we're going to take, in the concat statement there, we're going to take the key that we're passed in, and we're simply going to put in the binary key tag. And that B class key tag, that's where we've taken the point and we've concatenated it in a special way to implement the NPC byte array keys. We're going to set the state of this to be putted, so that everything that's actually in storage has a state of putted. And you can see that we're putting the state, and then we're putting the X, and then we're putting the Y. And again, we have to make sure that everything is converted to one of the three types that are supported, so either big integer, byte array, or string. And we can see that taking place there for the underscore state system field. So when we use this in our application code, we're just going to say point, class name point dot put. We're going to pass in the point, and we're going to pass in the key. It makes for very elegant, clean code and wraps up a lot of stuff that we don't have to worry about. Here's get. Get is a little more complicated because we have to test to see if the thing exists. And if it exists, then we have to kind of reconstitute or rehydrate, in this case, the point object from the individual values that are in storage. So again, at the top there, we're passing in the byte key, and then for each of these, get and put, there's a corresponding string version of the key, which I don't believe I'm going to show you. Key.length is 0. We're going to return, there we see we're returning the null object. And so if you get the null object back from a get call, that tells you that you had a bad key. We get a hold of the context, then we create again the binary key tag with the key that's passed in, plus the suffix that it defines this as a point. We create our variable p, and we're going to go out and do a get on Neo storage, looking for the underscore status field. If we don't find it in storage, it means the point doesn't exist under that key. So if bsta.length equals 0, then we're going to return you the missing point, saying no, we couldn't find it in storage. If the status comes back and it is non-zero, it means that the point is there and that we can assume the other fields are there. So we get the extension, again, just to follow through on what we've been doing all along. We convert the status that we had to an integer. We're going to convert it then to an entity, and we should be using our helper method here. And then we start to create the point. We create the x, turn the x into a big integer, the y into a big integer after we get it back from storage, and then we set the underscore x, underscore y, and underscore state values. And finally, we set override actually the state at that point to say that it's getted. So there's a few peculiarities there. But again, we're in the make it work stage of delivering version 1 of the MPC framework. So that's get. Okay, deletable. So as I mentioned when we were looking at the storage class, the Neo storage class, I had kind of overlooked that there was a delete method and had this strange craving to implement tombstoning. So this is going to show you the brewery method and how tombstoning is implemented at level 3. For those of you that aren't familiar with tombstoning, it's often used in environments where you have replicated data, like let's say Active Directory, where directory information is being replicated across a number of Active Directory domain servers. And there may be replicas of a particular object floating around in the replication network. And so you can't just delete something. What you have to do is mark it as deleted, and we call that tombstoning. It's like putting a tombstone on top of the entity so that we know it's not there or not supposed to be there, but we're not ready to physically delete the entity. And that's the strategy that we're using here for what we call burying an entity. So all we're doing is adding another state, and the entity, that's cool, is buried. So here's where we check to see if the state is tombstoned or not, and we can actually, create a tombstone object, and we'll see how those are used when it comes to the bury method. So bury here, again, there's a version of bury that takes a binary or a byte key and a version that takes a string key. There's also a version later on that will take a Neo storage key. So you see that the pattern here is very similar actually to a get. Before we can bury something, we have to actually find out if it's there or not. So if it's not there, we're going to return the missing object. Otherwise, what we're going to do is create a tombstone. And if you remember on the previous slide, a tombstone reinitializes everything to 0. And then what we're going to do is we're going to save that into storage. That's what those next 3 put statements do. And so this not only is going to tombstone it, it's actually going to 0 it out as well. Having realized that there's a storage.delete method, this implementation will likely change so that tombstone just marks it as tombstone and doesn't actually overwrite the data, because if you want to overwrite the data or hide or delete the data, you'll be able to call the delete method in the next version of NPC. So that makes it fairly easy to use. And these, of course, are very efficient. There's not a lot of code here. So we've not only found a nice way to express ourselves when we're writing applications, but the implementation, execution time implementation is very efficient from a code size perspective, as well as an execution time perspective. Level 4, collectible. So collectible is where we implement these strange beasts called network storage keys. So nothing really needed to change too much here in the Neo entity model. You'll see that in addition to tombstone, there's another thing called not authorized. That's looking to something that we have in the roadmap to be able to do authorization based on the user that's invoking the smart contract, being able to control what persisted entities that caller has access to. So that's not supported in this level 4. But it's snuck in on this to the slide. And at the bottom, we also have created some static read-only byte arrays for null script hash and null byte array. Just some utility variables that will help us support the implementation of Neo storage keys. Here's a brand new class, a brand new utility or internal class called Neo versioned appuser. That's a mouthful. And really the whole idea of the collectible level of support is to be able to have something better than just simple string keys or simple byte keys. And I should have a slide for this. I'm actually going to do a third presentation that's going to go into these a lot more deeply. But if you think of the value, the x coordinate of a point, it lives almost within a namespace. So x lives within a point object. There may be an array of point objects. So it might also have an index or an element. That element might live within a particular user context. The invoking user, and then that user might be running a particular application. So going from the top down, the outer scope is what is the application that owns this data, and we have the app name, the major, minor, and build number for that application. We have a particular user that's using that, and we identify them by their script hash. And you don't see it here, but the full implementation of Neo storage keys goes down to the class type and then the index within that class. We'll explore that some more. But we start off with this helper thing called Neo versioned user. It's a versioned application, a user within a versioned application. And we have a bunch of set and get methods for each one of those methods, so there's nothing too interesting there. At the bottom we have methods where you pass in all the parameters, basically the app name, the major, minor, build, and the script hash. So this is just getters and setters like we saw for the point class. Here is Neo storage key. So you can see that it is similar to a versioned app user in that it has the same first 5 fields, but it also has the class name, index, and the field name. These are all the properties needed to key or specifically identify an atomic value in Neo storage. So for example, if we think of an x coordinate having the value 10, we're going to store 10 as the value, and the field name will be x. The index will be whatever it needs to be, 0, 1, 100, 1,000, 1,000,000. The class name, the user script hash, the build, etc., all the way back up. Again, a third video talking about Neo storage keys and Neo Kong, the key object notation for geeks, will be discussed there. So here's how we create a new storage key. We pass in a new versioned app user object and the class name, and here we copy those values over from the Neo versioned app user, the VAU. And here we see the first example of not just defining these public static methods, but how you use them. So we can see that we've defined a class previously called the Neo versioned app user, and then we've got public static methods like get app name as byte array, get major, get minor, get build, get script hash, and we pass in the name of the object. So if we are using full C# for building a conventional Windows desktop application, we would be using VAU and dot the method name. That's not supported in C#.neo, so this is the alternative way, and it ends up being fairly elegant and fairly clean. Here's a bunch of helper methods. Again, I'm giving like a complete code dump, almost a complete code review here of how NPC is implemented. So there's a bunch of characters here that are represented as byte arrays. This is used for composing the Neo storage key using the Neo Kong format, and we'll see an example of that in a minute. In fact, we see it right here. So it looks like a lot, but basically what we're doing is just, for example, taking a left brace and the letter A followed by a colon, and then we're putting the type, whether it's string, byte array, integer, and then an equal sign, and then the name of the app, the string representing the app, followed by a semicolon, and this repeats itself. So it kind of looks a little bit like binary JSON, and there was some inspiration there from the BSON specification. But this encodes all of those fields that we saw before into a single byte array. And for me, this is really at the core and the heart of the MPC framework, how we encode and use these storage keys. So let's look at the methods that need to be defined for each object, for each class of object. There's bury element, put element, and set element. So the suffix, element, like brewery element, means that this is the not just brewery that takes a string or a byte array. It's the version of brewery that takes a network storage key, and you pass in the network versioned appuser, because the reason why the fields of the network storage key were refactored into the Neo versioned appuser is these are the fields that are invariant within an application, because the application name doesn't change once it starts, and the user doesn't change once a particular invocation of the smart contract has taken place. So the only variable part is the index, and of course, if we're talking about set, we'd be passing in a value as well. So here, what we're saying is go out and find the element that has that network versioned appuser with this index value and bury it. And so we have a special, we have the new method there where we pass the VUAN, and it's a point, and that should not be using a string. That should be using the the predefined constant. And we go through and use that key in storage and bring things back. So it's really just the computation of the Neo storage key based on the versioned appuser that makes this different from plain old brewery. So let's look at some test results. So part of the NPC DAP is these 6 test cases that can be executed. And we'll go through each one of them and explain them, I guess, as we go. By looking at the test cases, you'll be able to see the style of object-oriented programming that's supported. You can appreciate the nice clean syntax, and again, it gives you some. All of these calls, for example, to neo trace.trace end up in the event. Methods don't do anything with storage, so nothing happens in storage. This is just there for completeness. The second test case here, here's where you can see how we're making a point P0. We're setting it, we're resetting it, we're logging it. Then we make a P1. We call point.new. We set P1 to the coordinates x equals 2, y equals 4, and we log that point into the event log. We make a line, and we add 2 points. So this is just showing at the basic level, level 1 basic, what we can do in terms of manipulating points. And there we see the output in the event log. I'm not going to explain too much of that. If you want to click on this, if you're watching this on YouTube, you can click on the screen and take a few minutes to read that. Again, nothing in the storage viewer. Level 3, this is where we are using the persistent layer for the first time. So in the bottom half of this screen, you can see we're putting point 1, putting point 2, and putting point 3, and then we get point 1, get point 2, and get point 3. These particular examples are using string keys, simple string keys. You can see the quote P1, double quote, quote P2, double quote, etc. So again, very nice, elegant way, syntactically very clean, for using object-oriented development. This is assuming, of course, that you've implemented your classes, that you've followed the patterns prescribed before, that you've used the standard method names and have taken the time to do that. That may seem laborious. I'm going to talk in the roadmap section about how we make that better. So there we can see those gets and puts taking place. If you look in the bottom half of the screen here, you can see how the keys are actually being composed. So you see P1 /# point dot, and then the field name X or Y or whatever would be added to that when you look at it in storage. So here we're looking at it in storage, and you see the storage keys for the basic persistable level, where we're just using strings or byte arrays for the keys. Don't worry about these guys that have nothing in the content field, the content column. That's just how the storage viewer displays zeros currently. Here's another simple test where I'm testing querying with a null key, a zero length key. And so we should expect to get a null point back. And so there you can see how, is null is called, and we're passing it the point object that we received from get. We also have is missing and is extended. So down here we're looking for a missing key. And so the string missing P doesn't exist in storage, so we should get a missing object back. And we'll test again on the missing P to see if it's is null, is missing, or is extended. Again, extended is part of the on the roadmap for some future work, and that's the ability to extend the number of properties that are available for an entity. And so sometimes when you pull an object back, you may want to test to see if it's been extended, so that you can go back and ask for the values of the extended properties. That's not implemented in version 1.0. Just the extended method is implemented. And here, when we look at the event log, the same, just the Boolean values true and false are coming out, and they have the appropriate values, and nothing in the storage viewer. Here is where we go to the level 5 or level 4 collectible layer. And so the collectible layer is where we're using Neo storage keys, and we can support indexed collections of objects. So down here where we see index equals 24, just below that, we're going to put index equals 24 out into the trace, and then we're going to take the point P4 that we created above, and the versioned app user object we created above, and that index of 24, and we're going to put that out into storage. So you can see that it's pretty clean and simple to use collectible keys and at this higher level. So we going to put 24 at index 25 again, and then we're going to go down and we're going to do get element on those to get them back. And you can see that happen. So let's look at the trace here. Just underneath where it says test network storage keys, we can see that we're creating a new point, and it was initialized, and we dump out point 4 that has the the 10 and the 14. Right in the middle there, you can get an idea of what a network storage key looks like. It's pretty small print, but if you see the lines that have $BSK in them, $BSK, those are lines that are network storage key, or excuse me, Neo storage keys. And the dollar followed by 3 letters is an extension that was added to the event log in Neo GUI, and it's a format directive. It says rather than just treat this as a binary string, I explicitly want you to treat it as, in this case, a binary storage key, and do some special parsing. So that's why it appears partially parsed like this, and not just as a byte array. And here's what the keys actually look like when they're in storage. So they're relatively efficient. They're all byte arrays, and part of a substantially higher NPC level is the ability to do further optimization on these keys, a way of compressing these keys to probably half their size. So it's still quite an efficient way to represent things. The last test here, as we get close to the end, is actually 2 pages of code. So we're just dumping out some script hash stuff here, which isn't so interesting. At the bottom, we're creating a point P4 with the values 10 and 12. And then here we're looping through, from 30 to 40, and we're putting updated values of the point P4 at each of those indices. We're just before the put element, we're setting the x coordinate of P4 to be plus index and the y coordinate to be minus index, and then we're putting those. In the next loop, after all this work was done and after my DApp was submitted, I actually found that there's a bug in this loop. It actually is working. It actually gets the element using the same version appuser object, and it goes through the same indices from 30 to 40. But I'm going to leave it as an exercise for the reader to actually figure out what the bug is. In the if statement, we're taking the point and we're checking to see if the x is equal to plus index and the y is equal to minus index. Again, this is a test case to make sure that the framework is working. And that's the last test case. And we can see, all the storage keys dumped out here and all the script stuff at the top. You can feel free to click on, the YouTube video to stop it if you want to look at this a little bit further. And there's the results in the debugger. Okay, the roadmap section. We're almost at the end. So what are the things that we're anticipating for the roadmap? The next cool thing, and the thing that will really make this practical, is automatic code generation of NPC classes. And I've got a slide where I'm going to talk about that. We need to add support for storage.delete. It was simply overlooked, as I said. There's the level 5 extendable, but the ability to support entity extension capabilities for existing entities living in a deployed smart contract. So let's say we deployed that point NPC Persistable class. It has X and Y. Well, let's say you wanted to add a Z. How would you do that? We've got a really slick way of doing that in the extendable level. Authorize is the ability to support authenticated and role-based authorization that in 2 entities you create or possibly others have created. That leverages the Neo storage key capability and the fact that we have user script hashes embedded there. And then level 7 optimized, where we're going to do key space optimization. So that's Neo storage key space optimizations. And we have some interesting designs for that. In terms of automatic code generation, if we think back to that early slide where we talked about the Neo developer environment and how the Visual Studio C compiler creates MSIL, and the MSIL then is transcompiled into Neo bytecode. This, what I call the NPC compiler, npcc.exe, would take a simple class definition like you see here. You'd use the Visual Studio compiler to compile it into a DLL. NPCC would read the DLL representation, assembly DLL representation of this class you see here, it would inspect the DLL to find that there's a class called point and that there's two fields, one called _x and one _y of type integer, big integer. And it would automatically generate C# code for the NPC class. And one of the parameters you'd pass to NPCC besides the name of the DLL is what level of support you'd like to have. So let's say you want, persistable level. So, basic managed persistable. Well, you'd say I want persistable support for the, this point function, and NPCC would generate all the C# code for you. I maybe should have highlighted it before, but although all the code you've seen so far is hand coded, it's been extremely rigorously coded in the sense that it was designed to be, or designed with the anticipation of being automatically code generated. At the bottom there, just really some notes to myself, there'd be an NPC config class that you could also put in your source file for your basic class for passing NPCC configuration parameters. And then we need to do some investigation for partial class support in C#.neo and see if we can adopt that as a capability in C#.npc, because that would make this code generation fairly slick. Okay, so just in summarizing, we'll do one last sidebar. This was an interesting lunch the other day, actually. So what is this a picture of? Well, it's actually an architecture for a global Neo blockchain app. The spoons represent actors. The beer coasters represent personas that they might have on the blockchain. The sweet and low sugar packets on the far side represent the personas for the other user, represented by the spoon. That little lucite thing represents an authenticated user. That's their identity. And of course, in the middle, the phone and that red card, those represent apps that are running on the blockchain. I included this, it's totally frivolous. So in summary, I've talked about the complete design and implementation of the Neo Persistable class framework, including all the levels from 0 through 4. I've highlighted the rationale for how the design was chosen based on our analysis of the C#.neo language and what is supported by the Neo compiler versus what's supported by the Microsoft compiler. And I think we've created something pretty cool here. The appendices. Well, I'm just going to flip through them out at this URL in the MW Herman /neo-charm project, where you can read more about that. More diagrams with annotations, drill down diagrams, and finally we're done. So if you have any questions, you can find me on Discord, Michael Herman in Toronto, or you can send me an email at the address you see here. I know this has been a long slug, about an hour and 25 minutes. I appreciate your time, and I look forward to your feedback. Licensing and copyright. The Neo Persistent Class Framework is copyright by myself, Michael Herman, and it's licensed under the MIT license.